Hello interwebs, welcome to Let's Fix Computers. I've got a HP Omen here that does not power on. So this is going to be the usual song and dance, I believe. So let's open this thing up and I'm going to show you how we can diagnose it and how to approach this problem in full, I guess. From previous videos, people really like it when I do that full walkthrough thing, so I'm going to try and make a conscious effort to do that this time around. Let's see how we go. So, first things first, I don't actually have the charger for this laptop, so I'm hoping that the battery's got some juice in it. Otherwise, I'm going to have to get creative, I guess. What charger does this actually take? I might have something that will go in there. Maybe not enough for it, but it'll be something. Anyway, let's get the back cover off, and we're going to have a look and assess the board first. So, screws out, pry the back cover off. Okay, so first we're going to disconnect the battery. So we'll just unplug that guy down there. So before we get too deep into taking this thing apart, we kind of want to do an initial confidence test. We want to see if this thing is likely to be a waste of time or if it's likely to be something fixable. And the way that we can do that is just check for a main rail short. So what is a main rail short? What is a main rail? Okay, so in a laptop, we have multiple voltage rails that power things in the laptop. So the main power sources are, we've got the main battery here and we've got a DC in cable here. So this DC in cable is huge because this is a big ass gaming laptop with a high wattage input. So we've got two possible power inputs here, and then these things will go through some kind of regulation and will become a main power rail. And there are a couple of different types of main rails, which I'm not going to go into in this video, but I do plan to go into further in future videos. But for the time being, the point is they become some kind of regulated power rail called the main rail. Then from that main rail, we have secondary power supplies for things like a 5-volt rail, a 3.3 volt rail, a 1-volt rail, and so on. And there'll be like a memory power rail, and there'll be the backlight power rail for the screen and things like that. And the main rail is where you're going to see problems most often because that is the sort of big high voltage heavy lifting rail that's doing all the work. There's more power there, so it's more likely for things to fatigue and fail. So we want to check that. So how can we find it? Well, we can start following the input from the DC input or from the battery input, but for most laptops, it's usually really easy to find a spot to measure the main rail just by going to places where it's going to be used. And on pretty much any laptop, the secondary power supplies for the CPU and the GPU, known as CPU Vcore and GPU Vcore, those are going to be powered from the main rail, and there's probably going to be a whole bunch of capacitors somewhere nearby. So if we take this laptop as an example, let's just zoom in a little bit. You can see that we've got some big electrolytic caps here and here. And written on these caps, it says that it's a 25-volt capacitor. It's got 25V on it. Now, a lot of components on the board on modern laptops don't have their values written on them directly like this, so you can't rely on that. But if you do see big capacitors like this that have a voltage written on them, then you're getting information. And 25 volts, there's only going to be one rail on the motherboard that is going to be anywhere near that kind of voltage, and that's the main power rail, which is going to be generally somewhere between 10 and 20 volts, depending on the setup for this particular board. So we can straight away pretty safely assume that these 25-volt capacitors are on the main power rail. And if we have a quick look here, you can see that you can just see patterns here of more capacitors where we've got probably GPU Vcore here feeding into the GPU. We'll see more when we take this off, but just straight away, just by having a look, we can see there's probably power down there. So let's measure this capacitor. That's going to be our main rail, and let's see if we have a main rail short. So I'll put my multimeter into resistance mode. So we're measuring ohms, and we're going to check the resistance from the main power rail to ground. Now, an electrolytic capacitor like this, a big can style one, the stripe is the negative, and then there is a notch. There is a notch on the positive sides. So I'm going to go negative to positive here. And when we measure that, we see 0.14 ohms. So that is a resistance of 0.14 ohms between the main power rail and ground. That's functionally nil. That's basically nothing. We're looking for less than 0. And what we've got here is extremely less than 0. So we've got a big short on the main power rail here. Now, this is good news for us. A big, massive main rail short like this is very likely to be the classic failed capacitor problem. What we don't want to see is low resistance, like a couple of ohms. Like if we're seeing, if I was seeing values of like, 1, 2, 3, or 4 ohms above 1, but still extremely low, then that would be a very bad sign, and I'll elaborate more on that in a minute. If there was no short at all, I would expect to see thousands of kilo ohm, hundreds of kilo ohms or mega ohms of resistance. It would be extremely high resistance. So we've got a main rail short. So low resistance would be bad, because if we saw a couple of ohms resistance, there's a very good chance that that would be a high side short. So one of the MOSFETs powering the CPU had shorted out, and we were seeing a path from the main rail through that shorted MOSFET, through the CPU, and into ground. So we'd be finding a path through the CPU, and that probably means our CPU is already dead. So a couple of ohms, really bad. Less than 1 ohm, really good. The other exception to this is the GPU is really low resistance, like 0.4 ohms, that kind of thing. So if we were seeing like maybe sort of, half an ohm of resistance, that would be a little bit shaky ground. But also when you're measuring resistances this low, like half an ohm, we start running into issues with probing, where if you've got some nice sharp probes and you're stabbing onto actual solder joins, so the probes can really dig into the solder, you can measure really low values. But for example, if I put my black probe onto this USB port, so it's just on some tin shield, it's going to get less of a good connection there, because the surface area between the probe and the metal is really low. So if I measure across like this, see how I'm seeing a high resistance? Now I'm seeing like 0.5 ohms kind of thing. And it's kind of wandering a bit because I don't have a great connection. Whereas again, if I put my black probe on like a big solder blob on the back of a different capacitor and measure again, now we're back down to like 0.18, 0.16, because we've got a really good connection there. So you can see how at this point probing starts to matter, because that's the difference between going, oh, is that a GPU short or not? But also, you might have a short that is just genuinely like 0.6 or 0.7 ohms. And so if you see that, we don't completely rule out the GPU, but we'll do some more measurements in a moment that can confirm that. So either way, we found a main rail short. This looks like we're getting somewhere. So let's get the motherboard out of the laptop so we can look at it properly. So now we're going to disassemble the laptop. I'm going to roll the intro first, so I'll see you guys after the cut and we'll get into it. I think we're ready for this to come out, so let's just do a test lift. Feeling good so far. Just gently lifting to see if anything is snagging. I think we're just hung up on the ports now, which just sometimes need to be jiggled a bit. There we go. Right. So before I do anything, I'm just going to look at the back of the motherboard. And I'm just looking for signs of distress. What we're seeing mostly in this is what I call honest dust. Laptops get dusty. That's just normal. That's what happens. So seeing dust like that is, that's fine. What we don't want to see is like burn marks, corrosion, tide marks where there's been liquid, that kind of thing. So I'm just sort of looking around, just looking for any obvious issues. You don't always get lucky enough to be able to spot the problem, but sometimes just, if you take the board out and just look at it, you might just see something immediately and go, oh, okay, that's clearly a burnt out component. And I'm not seeing anything at first blush, so let's keep going. So I'll get the body of the laptop out of the way now. So now we've got this motherboard out. At this point, it's a good idea to try and sort of familiarize yourself with the board and sort of look at it and understand it and start looking for patterns. And when I say looking for patterns, look for things that you can recognize, shapes and layouts that are familiar or you can familiarize yourself with to help you recognize them in the future. And we can start with basic stuff. Like, for example, if we look down here, this is where we took off a little bit of coverage there. You can look at this chip here where my finger is pointing, and you can see that there's traces that go up and around to the Type-C port. So just straight away here, we can identify that this is our Thunderbolt controller because it's a chip that's connected directly to the Thunderbolt port. And underneath that, it's got a little ROM chip that stores the Thunderbolt firmware. So immediately we start looking at things and going, okay, this section is Thunderbolt. So that's our Thunderbolt section. And, at the USB ports, we can see traces that go off to other chips, and you can start looking and seeing different subsections of the board. So that's what I mean by sort of looking for patterns and understanding things. Now, obviously, a lot of this stuff, like Thunderbolt, this isn't relevant to us. But by looking at it and just seeing patterns, seeing where traces are going, we can start understanding the board. And we can be doing all of this without schematics or a board view either. Having schematics and a board view is great, and it's a great way to study. But I try to drill this into people that you can get really far just by using your eyes and using your observations to get an idea of what's going on. Because more often than not, a lot of these things you can get really far without the schematics. What about the power system then? Well, let's have a look and see how that works. So we had our big DC-in cable coming down and plugging in here. So let's take a closer look and let's follow the power through the board. So we start off by coming into this big DC-in jack, and straight away we go into these dual MOSFETs here. So these are two DC-in MOSFETs. There's two of them for power tolerance basically, because there's a lot of wattage coming into this thing. So we go through a pair of those in parallel, and we go onto this big pad here, and you can see that that pad has lots of dots on it. So those are vias. That's a pathway through the board. So if we flip the board over, those come up there. So that's where we just came through the board, and we go through a second DC-in MOSFET. So those two this trio of DC-in MOSFETs, we've got a pair of them and then a second DC-in MOSFET. These two provide a switch and controlled flow of power into the board. Pretty much all laptops will have DC-in MOSFETs like this. It's unusual to see a pair of them at the start point, but again, that's because we've got a very high power laptop here. Most laptops will have a single one of these, then going into the secondary DC-in MOSFET. Once we've gone through that MOSFET, we immediately do a U-turn into this big black package here. And that is a current sense resistor. So if we take a closer look, you can see that says R005 on it. So let's measure that and see what the resistance on it is. And as you can see, it's about 0.06 ohms there. and it said R005, so that's 0.05, but that's a really low resistance and it's extremely difficult to get good enough probing to get down that low. So that's a 0.05 ohm resistor. So what this does is this is a current sense resistor, and you can see that we go through that resistor and there's two little lines just coming out the side of it there that then go off down here toward somewhere else, probably all the way down here. And so what's going on here is this current sense resistor, power goes straight through it, and because it's 0.05 ohms, it provides functionally zero resistance. However, that 0.05 ohms does provide a tiny amount of resistance that's going to induce a very, very slight decrease in voltage across this resistor. And that voltage decrease will get more as we draw more current, more watts through into the laptop. So the power chip down here is watching this resistor, and it's watching that tiny drop of voltage across it, and that allows it to measure how much power the laptop is taking in, so it can detect if there is too much power. Now, incidentally, this is why the laptop won't turn on, because as soon as the laptop tries to turn on with a main rail short, it will try to draw unlimited power, as much power as the power supply will deliver. So this current sense resistor and the power management chip is immediately detecting a fault and going cut the power. So it then switches off these DC in MOSFETs, preventing further damage to the laptop, in theory. So we've come into the laptop, we've gone through our DC in MOSFETs, and we've gone through a current sense resistor. And now, as you can see, we've become this big fat power plane here. And we can follow this all across the board. It's a big artery that goes all the way across the bottom, goes all the way down here, up to here, and then there's another resistor there. That's another current sense resistor that then goes into this section of the board. And if we flip that over, that's this section here. So now we've gone into GPU Vcore. This is the power system for the GPU, which is there. Now I'll talk a little bit more about that in a moment, but you can see how we're now following the power around the board. We've also got some vias there, so it's taking a stop off there as well, and that's coming up here, and here is where the battery plugs in. So we've also got some more MOSFETs and power system for how the battery connects into the main rail. And so we can charge the battery through this MOSFET, or the battery can power the rail through that MOSFET. So that's where that connects in. And then finally, as well as going along the bottom of the laptop here, we're also coming up the side all the way up to the top here and into this section. And there we find our CPU Vcore. Here's the power system for the CPU. And again, we'll look at that again in a moment. So by having just a simple look across the board like this, you can see how we've started understanding the layout of this board and how the power structure works on it. So in addition to that main power rail that is going across the board and powering our GPU Vcore and our CPU Vcore, we also have more secondary power supplies down here. Let's take a look at these next. So I mentioned earlier on that we have secondary power rails for things like 5 volts, 3.3 volts, and so on. And the big giveaway for these secondary power supplies is that they always have an inductor on them. So the way that a power regulator will work in a laptop is that you have a regulator chip, so like this chip here, and that will be going into an inductor, and then around it at the input and output, you'll have a whole bunch of capacitors. So you can see we've got these little brown ceramic capacitors. There's a tantalum capacitor there as well, and so on. So if we look for this one, there's a regulator chip, an inductor, and there's capacitors all around it. Regulator, inductor, capacitors, regulator, inductor, capacitors, regulator, inductor, capacitors. So you can see where we've got secondary power supplies down here. And there's going to be more of them elsewhere as well. Like, for example, there's another one down here near GPU Vcore. This one's probably doing the Wi-Fi power. And we could probably find more of them that might be doing like this M.2 port and things like that. They'll be all over the place. So right now we know that we have a short on our main power rail, and what we want to know is if that fault is just on the main power rail or if it is going to other places in the laptop as well, like those secondary rails. So let's measure our secondary rails and see if we can see any cause for concern. Now the secondary power rails will have a lot of varying resistances on them, but pretty much we're looking for zero. We're looking for anything that is 0 ohms to ground. So I'm going to take my black probe and I'm going to put it on the negative side of a big capacitor. So I've got a good ground connection there. And now I'm just going to touch all of these inductors and just see what the resistance to ground is there. So we've got 146 ohms. We had some meg ohms there and then it just went over limit, so that's very high resistance. We've got 15 kilo ohms. We've got, about 11 kilo ohms. Okay. Let's get this. That's the battery, so that's not going to be an issue. I mean, we'll check it anyway, because again, it shouldn't be short. Yep, cool. Kilo ohms there. Check this guy over here. Yep, again, that's in the kilo ohms range. All right. So all of those secondary power rails seem good. Now, if you know particular motherboards or particular platforms very well, then you may be able to start memorizing specific resistances for the secondary power rails, and you'll be able to know if there's anything up with those. However, they do vary between different motherboards and platforms and generations and stuff like that. So memorizing exact numbers, not really useful for a beginner. Really what we're looking for is anything that's reading 0 ohms to ground. If we saw any of these at 0 ohms, that would imply that there is a short from the main power rail through that secondary rail into something on the secondary rail. And that's really important because it means that our problem probably isn't on the main rail at all. That's a symptom. So for the time being, we're not seeing any shorts on our secondary rails, so we're pretty confident that those are okay. So now we need to take a look at the Vcore rails to check if those are okay. So what we're going to do for this is we're going to take a closer look at CPU Vcore. So underneath this goop here, we've got some MOSFETs, and that might be a dual MOSFET package. It might be DR MOSFETs. It might be power stages. It doesn't particularly matter. It's some kind of MOSFET package. And just like with the secondary rails, next to them we have inductors, and we've got capacitors all around as well. Not a huge amount of capacitors here. A lot of them are going to be on the back of the board, I would imagine. Yeah, there's some big capacitors on the back. So there's our bulk decoupling. And the back of the CPU itself has lots of capacitors on it as well. So our power is coming in, it's going through these MOSFETs, through the inductors, and then into the CPU. So what we want to do is we want to check if there's any problems in this area. The MOSFETs should function as a barrier between the main power rail and the CPU because they're stepping the voltage down from the high voltage main rail to the low voltage high current CPU rail. So let's have a look. Now, I mentioned earlier on that the CPU and the GPU themselves will be very low resistance. So when we measure these, we're expecting to see something pretty low. So once again, I'm going to stab the back of this big capacitor down here as my ground point. And if we measure one of these inductors, we get about 15 ohms. I'm going to check the other one just to make sure I've got a good connection. Yep. So we've got 15 ohms. So that's very low. And it's not uncommon to see CPUs as low as like 3 ohms. However, it's not 0. It's not 0, and it's not the same as what we're seeing on the main power rail. If we go back to one of our shorted capacitors here, again, we can measure that, and we get actually 0, 0.11 there. Really low. And so let's just check these other inductors. These three are all going to be paired up together. These are all working in parallel. Then we've got some extra rails over here. So that's another one. That's 15. That's probably parallel as well. And then we're going to have some auxiliary rails, 53 ohms. So again, there's another sort of low resistance, but not 0 there. Cool. Let's go over to the GPU. So for the GPU Vcore area, you can see we've got even more power phases here. Again, we've got some MOSFETs, inductors, and then it goes up into the GPU. So if we measure one of these, we're going to see GPU Vcore. Oh, look at that, and it's 0.25. It's a quarter of an ohm. So that's really low. But also, remember, our short is down at like 0.11 kind of thing. So it's not the same as the short. But again, at these kind of resistances, you want to make sure you've got some good probes on your multimeter and that you're stabbing nice big solder blobs so you're getting a good connection. So if we check that one again, I'll just grab another one at random. There you go, we've got about 0.25 ohms, and that's not the same as the capacitor, which immediately drops down to, again, I'm struggling to get a good connection on that, but it's trying to go lower. It's trying to go down. We've got 0.18, 0.19 there. So at this point, we can be confident that we don't have a short through any of these. If we saw the same resistance on GPU Vcore or CPU Vcore as we did at our shorted main rail, that would probably mean that one of these MOSFETs had shorted through, and we were shorting through the main rail, through one of the MOSFETs, through the GPU, and into ground. And that probably means the GPU would be dead. So at this point, we're confident that CPU Vcore and GPU Vcore are also okay. So we've checked our secondary rails, we've checked our Vcore rails, and we haven't seen any cause for concern. There's one more I didn't check up here, and that's this guy here. That's some kind of secondary rail again. So let's just quickly stab that. So we'll go ground point and that inductor. And we've got about 1.2K there. So again, it's not zero. It's all good. It's fine. We've also got one here that we missed. This is probably memory Vcore for the VRAM. So let's get that guy as well. Ground point and the inductor. About 46, 47 ohms. So again, it's low, but it's not zero. So we're pretty happy that none of our guys are problematic here. So we've established that we've got a main rail short, and that short hasn't spread to any other subsystems that we've checked. And we've checked all of the usual suspects. There are always lots of smaller areas that we could go looking at, but those aren't areas that typically fail. So I'm not going to go into all of the weeds here. But right now, we're pretty confident that we've got a main rail short that is isolated to just the main rail. So this looks pretty straightforward so far. So where's the short then? The main rail, as we've already established, goes all over the board. So how do we know which part has shorted? Because there's capacitors everywhere. There's components everywhere connected to the main rail. Well, the classic way of discovering it is to use power injection, sometimes known as voltage injection or current injection. You can argue in the comments. I just call it power injection because we're injecting power. So when we inject power, what we do is we apply power to the shorted rail, and that power is going to look for a path to ground, and it's going to find a path to ground through the shorted component, and that component will heat up because we're passing power through it. So if we start injecting power, something on the board will get hot as it passes the power to ground, and then we can use a thermal camera to see what component is getting hot, and that tells us which bit has failed. Now, I have a pretty good guess already as to where I'm going to find the fault, because I've seen a board very similar to this one before, and I know exactly where the fault was, and when I've been looking over the board, I've already spotted a particular point that I'm pretty certain is going to be it. But just for the sake of the video, I'm going to keep going regardless, because if I haven't spotted it, who knows? Now, once you've found the faulty capacitor, it'll kind of stick out like a sore thumb, but for the most part, it's really hard to spot them because there's so many. Like, if I just come in under the microscope here, if we just start looking at random capacitors here and looking for ones that have cracks in them or look discolored or something like that, there's a lot of them, and there's a lot of them to look at. And it can get into your head because, like, you look at like that one there, that kind of looks like it's got a bar across the middle of it. Is that a fault? Is that a problem? And lots of capacitors will look discolored as well. If we come up here to CPU Vcore, these guys have got some dust around them. We could start getting to these. We could clean them up and look real close. Could be any of those guys. That's got a dot on it. Is that a hole or is that just a scratch? What's that? Who knows? And you can spend all day looking at them, and it's worth a casual glance. It's worth a quick look around to see if you can spot something. But generally, you've got to be pretty lucky to actually see the faulty one. I'm not going to say that it's not worth looking across the board because, as I mentioned, I have already seen it. But I've got a trained eye, I've seen this one before, and I'm vaguely familiar with this motherboard, so I've got the advantage. But at this point, let's pretend that we've looked across the board, we haven't seen it, we don't know where it is. So we're going to inject power. Now, before we inject power, we have to consider the risks of injecting power. This board has an electrical fault on it, so we shouldn't be trying to power anything up on it at all. So we need to consider, are we going to damage anything by injecting power? Well, we've got a fault on the main rail. The main rail is shorted to ground. It has 0 ohms resistance to ground, and that's not right. It should be thousands of ohms. So we know we found a problem, and we know that voltage injection is going to help us find that because it's going to pass power through the faulty component, make it heat up so we can find it. So injection is going to help us, and we know we're going to inject on the main rail. Could that do any damage? Well, we're going to inject at a low voltage. We're going to inject at 1 volt. And this power rail is rated for, about probably up to 20 volts because it's expecting 20 volts from the charger. So at 1 volt, we're not going to overpower the rail. And then we can say, okay, well, could that 1 volt go anywhere else? Well, it's not going to go into the CPU because we know we've already checked the CPU power supply, and that's all okay. The GPU power supply, that's okay. It's not going to go into the GPU. It's not going to go into any of the secondary power rails because none of those were shorted, so we know that's okay. So if we put 1 volt onto the main power rail, we're pretty certain that the only place that's going to go is our faulty component. So at this point, we're pretty confident that we're ready to inject. So let's do that. Let's inject power onto this motherboard. Now, in order to inject power, I've got this DC bench power supply here. This particular one is a Hanmatech HM305P, but bench power supplies come and go, so good luck finding this exact model, but it's a 30 volt 5 amp power supply that is programmable. So I can set the voltage to be anything I want, and I can set the current limit to be anything I want. And the important thing about that, so we can go up to 5 amps, or I'm going to stick at 3 amps for now. Now, the important thing about having a programmable power supply like this is that when we inject power, we're going to be injecting into a short circuit. Because there is 0 resistance from positive to negative, the power supply will also go into a dead short and attempt to deliver as much current as it can. So it's important that we have a power supply that can limit the current, so in which case we're saying you may not draw more than 3 amps. Now, if we were to try and do this with, say, a battery or a mobile phone charger or something like that, a power supply like that has no kind of current control on it. So as soon as it goes into a dead short, it will deliver as much current as the materials can handle and most likely damage the power supply, or in the case of a battery, that's really dangerous. You could just explode the battery doing that. Absolutely terrible idea to try and inject using a battery. So whereas with this one, because we've set a limit, we've said this is how much power you're allowed to draw. So if I switch on this power supply, now the output is turned on, and apparently I set it to 0 volts, so let's just set that back to 1 volt. There we go. So now if I touch the positive and negative of my power supply output together, as you can see, the power supply drops into a short circuit. We're pulling 3 amps, which is the limit we've got, and our voltage has dropped down to 600 millivolts here, 0.6 volts. Now, the reason why the voltage has gone down is that the outputs are connected together, so the potential difference between them must drop. And it drops based on the resistance in the connection. So there is resistance in the leads, there's resistance in this crocodile clip, and resistance in the probe. And that's why we don't drop to 0 volts. Theoretically, we would drop to 0 because there is no difference at all. The outputs are connected together. But in the real world, we have resistances in everything. So we drop to about, in this case, 0.54 volts. So that's what we're expecting to see when we go into a short circuit. And this can be deceiving for someone who's new to voltage injection because they start injecting and the voltage goes down. And they're like, well, I want to inject at 1 volt. So they try and increase the voltage, but the voltage doesn't go up because it can't, because you're in a short circuit. So this is what we're expecting to see. We are sending 1 volt, but the voltage drops down because we're in a short. Now, in order to put this voltage into the laptop, I'm going to connect this crocodile clip up to a ground point. I'm going to connect this up to this screw hole here. There's a nice big bit of copper that I can clamp onto. Try and get a good connection here. Okay. And now in order to do the injection, I'm going to touch the positive of one of these capacitors because we know that that is on the main power rail. So we'll be injecting into the power rail. And now to find the actual hotspot, I'm going to use my Infrared P2 Pro thermal camera. So I'll just plug that into my phone. All right, and it's really hard to avoid reflections on the screen for the camera, so I'll just hit record video here. And so now we've got thermal imaging of the board. So when something gets hot on the board, we'll see an orange spot light up. And we have to be a little bit careful of reflections. So for example, you can see there's something glowing there, but that's a screw hole where heat in the air, heat coming off my face, heat coming off my hand is bouncing off of that screw hole and up into the camera. So that's a reflection we're seeing. If I move the camera around, it goes away. So it's not a real heat source, it's a reflection. So now we've got that, let's just touch the capacitor and we'll see if we can see anything get hot. And we might have to move to a couple of places. So let's start out. So I've touched the board. The power supply has dropped into a short at 3 amps. And now I'm looking for something that's getting hot. And I'm not seeing anything over on the left side of the board. And there's some warmth up there. That's our ground probe. So we're going to get heat there because that's where the ground is connecting. There's power going through there, so that's normal. All right, my hand is covering everything in the bottom right, so I'm going to come off. Hey, you can see there's kind of a glow around there. Let's do that again. This time I'm going to put my hand at a different angle. Yeah, there you go. You can see we've got a warm area appearing here. Now, because that's very spread out, that's going to be on the other side of the motherboard. And that's heat coming through the board. So let's turn the board over. So we're looking in this area somewhere. Now, to inject on this side of the board, we can just inject directly onto the current sense resistor because that is part of the main power rail. Remember, we were looking at that earlier on? So let's inject directly onto that current sense resistor and see what lights up. There you go. So you can see we've got an actual pinprick dot there. Let's move in close. And at the moment, our vision goes a bit blurry here. So what I'll do, I'll come off and I'll put on the macro lens. Now I can get in really close and we can see the detail. And there we go. So there's a bunch of capacitors there, and you can see that one of them is lighting up. So that's getting hot because that 3 amps that we're pulling through the power supply, it's finding a path to ground through just that capacitor. This is overloading the capacitor, so it's burning up. You can see we've got a little bit of heat around where my probe is there as well, and that's just simply because the 3 amps is also passing through there. But one more time. Bam, straight away. And if we go right down here onto these capacitors, we can get really close. There we go. As a side note, I'll leave some links in the description down below to some of the tools that I've been using today, including this Infrared P2 Pro, which I think is still available, but I think this camera has actually been discontinued. But I've got a review coming up for another upcoming camera, so stay tuned for that one. And I'll throw in a link to the multimeter I use here as well, which is this Unity UT61E, and a couple of other bits and pieces. So if you want some ideas on the kind of tools to get, check those out. So the area we were looking at was here, just after our DC in MOSFETs, and it was this capacitor here. So let's just bring in the microscope and take a really close look at it. So our faulty capacitor was this guy here, the second one down. Now earlier on I bragged that I'd already spotted the faulty capacitor, but actually I was wrong. I thought it was this one, because if you put the board at a certain angle, can you see how the one on the end just looks ever so slightly discolored compared to the rest? So that's a good lesson in how like visual glances can be deceiving. You can spot a capacitor that looks really discolored compared to its neighbors and think that you've seen something, but actually it could be nothing. So can we see the fault on this dead one? Let's bring the board up and just zoom in there, or focus in. And there's the crack on the side of it. It might have been cracked before we injected it, or it might have cracked under the thermal stress that we just put it under. Either way, good luck spotting that. This is what I mean by do a visual inspection, but like if you don't spot it with your eyes, don't worry, because sometimes it'll be really obvious, and other times you will never be able to see it with the naked eye, no matter how confident you are. So I'm going to take off that row of capacitors. Now technically it's just that one that is faulty we need to remove. However, as of basically this week, I've kind of shifted gears now, and when I see a row of capacitors like that with a faulty one in it, I'm going to start replacing all of them. Considering these capacitors cost basically nothing, when I see 4 in a row like this, I'm going to replace all 4 of them, because if one of them has failed, there is a non-zero chance that the others might not be far behind. The microscope I'm using is a Tomlov 4K autofocus microscope, and again, I'll stick a link to that down below. I don't shill my stuff that hard, but also people ask me what I use, and product manufacturers do send me samples. And for example, this microscope, I haven't given it enough credit, but it's been really good. And as you can see, I get a really nice crystal clear picture out of it with no fringing around the edge or anything. Really great scope for people who don't want to get the big, huge dual binocular scopes set up on their bench. So to start out with, I'm going to use my soldering iron to just put some fresh solder on the side of these capacitors. So I've got my soldering iron at, I'm starting at 380 degrees, but we're on big power planes here. We've got a big main rail power plane here and a big heavy ground plane here. So these guys might fight us as I try to take them off. So we'll start at 380. We'll see if we need to go a bit higher. And I just want to flow fresh solder onto the sides of these capacitors. And this is leaded solder. So adding this leaded solder to the side is going to make the solder melt more easily when I try to actually remove them. I should turn the board around so I'm not working backhanded, but I try to keep things straight for the camera. There we go. All right, now I'm going to come in with my hot air station, and I'm going to set my hot air to 400 degrees maximum airflow, and we're just going to pick off those 4 capacitors. Here we go. Right, now I've got those capacitors lined up for a whodunit. I've just stuck them down on a bit of masking tape, and we're going to see which one of these guys is shorted. Now I'm replacing all of them, so it doesn't matter. However, we can go through and we can just confirm which one was the actual culprit and identify that it is dead. So if we check this guy, oh, there we go, first try. Well, there's the dead one. So that one is, there's our short circuit at 0.11 ohms. And these other ones now, if I measure these, we'll find that they'll initially be low resistance, but then they'll immediately shoot up to very high resistance. So we've got 15 mega ohms. And that's just immediately gone. Oh, there you go. Yeah, 200 mega ohms. Yeah, they almost instantaneously go over limit. And so what's happening is the multimeter probes are passing a very small amount of power between them to measure the resistance. And when we put the multimeter probes against the capacitor, the power going between the probes starts to charge up the capacitor. So as the capacitor absorbs power from the multimeter, we'll initially see a low resistance as power flows. And then as the capacitor saturates, it becomes fully charged, it goes high resistance as no more power flows. So on things this small, they'll charge up basically instantaneously. But on a big power rail where there's lots and lots of capacitors and big high capacity capacitors, it can take a while. So you might initially see a low resistance that then builds up. And that can be deceiving. But this guy down the bottom, that one is in a dead short circuit, and it doesn't change, it doesn't charge, it does nothing. So next question is, what value are these capacitors? So I'll move the multimeter into the capacitance position. So we're now measuring farads. And if we check this guy here, oops, I've just got to hold on to it. Oh, blimey. It's very difficult to probe tiny components like this. And we're seeing 22 microfarads. That little U symbol in the bottom right of the multimeter, that's the micro symbol. So that's 22 microfarads, which is an absolute classic size of capacitor. So these are 08, 05, 22 microfarad capacitors. Their voltage rating is probably 25 volts. And with a capacitor, the capacitor doesn't charge up to its rated voltage. It charges to whatever you put into it. So in this case, because our main power rail is, say, 20 volts from a USB-C charger or from the DC input, it will charge these capacitors up to 20 volts. But their rating of 25 volts, that's the maximum that they will tolerate. So remember we had the big electrolytic boys here? These ones are 25 volts, not because that's what they'll output, but that's the maximum voltage you can charge them up to without damaging them. So for a capacitor, you need to have the voltage rating of the capacitor needs to meet or exceed the rail that you're putting it on. So we need a capacitor that is at least 20 volts. And ideally, we want to have a bit of margin. So that's why these ones are 25 volts instead of 20, because you don't really want to be charging them up to their maximum rating. You want to have some overhead. So we want an 0805 22 microfarad 25 volt capacitor. Here's some I bought earlier from eBay. So these things are so common that I keep this strip of them on my bench because it's always 22 microfarads, or the other common one is 10 microfarads. So there's my strip of 10 microfarad capacitors. So if you keep a strip of 22 microfarad 0805 caps and 10 microfarad 0805, you'll fix a lot of laptops. So let's come under the microscope again and put 4 of these guys onto the board. So I'll just reveal 4 and then try and tip these out without sending them flying. Ah, they went flying. Okay, they didn't go far. Hold on. Now I'm just going to add some flux onto the board, and the flux is going to just make sure that solder reflows nicely, and it also just helps stick the capacitor down while we bring everything up to reflow temperature. because initially these capacitors are going to try and just blow away in the hot air stream. So I'll just put them into the flux. We don't need to worry if they're not perfectly aligned. They'll align themselves when we start flowing. The surface tension of the solder will just pull all of these into place. There we go. All right. Now I'm going to turn the airflow on my hot air station down a bit. I'm going to turn it down to about 2/3. And I'm going to start with the hot air fairly far away. So I'm quite high above the board. I'm just going to start warming that area up. Because as you can see, these things are going to try and just blow away in the airstream. So we'll just heat from a distance. Oh gosh, that bottom one really wants to escape. Oh, and it's off the board. Alright, hold on. Let's try and put you in the middle there. There we go. Try and bunch them up a bit. Okay, now we can start getting lower and lower. And as soon as that solder starts to melt, they'll all stick into it. There you go. Right, and now if we just give those a gentle nudge, the solder blobs will just pull all of those into alignment. There, beautiful. Now I'm going to use some isopropyl alcohol to clean the area up. So I'll just apply that to a Q-tip, and we're just going to just scrub around there, and we're just going to wipe up the excess flux. And now, just for good measure, we're just going to make sure that our short circuit is now resolved, which it better be, because we've kind of gone pretty far. I should have checked this after I took the capacitors off, but I forgot. So I'll put my black probe onto a ground point and red probe onto the current sense resistor. And as you can see, we're now seeing kiloohms of resistance there. And what I'll do now is, if we flip the board back over and we look at these two electrolytic capacitors, these are the guys that we first measured back at the start. So let's check those. So from the ground to the positive side, as you can see, we're now seeing kiloohms of resistance. That's still fairly low. And, 7.5 kiloohms of resistance, that seems a bit low for a main power rail to me. But this is what I was talking about with not knowing the exact resistances of each rail. The important thing is that it's up in the kiloohms range and it's no longer a dead short to ground. So that's the bit that I'm going to focus on. Let's get this back in the chassis. I'm going to rebuild the laptop and we'll try turning it on. Something we also need to check that I forgot to look at earlier on is the DC in MOSFETs and whether they are damaged or not. Because we've had a main rail short, there has been overcurrent coming into the laptop, and that can damage or kill these MOSFETs. And when they die, they will usually fail short, so they just become a wire straight through. And this can initially be difficult to spot because this won't prevent the laptop from turning on, but it will stop it from charging properly. And when I tested the laptop, we were testing it on battery power. So we haven't actually checked if these are okay. So let's have a quick look at those as well. If the laptop is charging, then there's a good chance that these are fine, and they don't usually blow. And because these are big boy MOSFETs, I'm not expecting them to fail, but we should check. So I'm going to set my multimeter into diode mode. So I've gone to, on a lot of multimeters, you go to resistance and then press your mode button until you get a diode symbol. And what we're going to do is we're going to check the diode drop through the MOSFETs. So let's start with this one here. So I'll put my black probe on the left side, red probe on the right. We're going to check in both directions. And in one direction, we should see over limit or open line, whatever. So no current is flowing. Cool. And if we check the other direction, we should see a diode drop. There we go. So now when we swap the probes around, we see a 0.5 volt diode drop through the body diode of the MOSFET. So that's normal behavior. That's what we expect to see. And we'll check the other one as well. This one should be the same deal. They're in parallel, so we should get identical readings here. But just for posterity. And then open line. Cool. There's also a MOSFET on the other side. We have our second DC in MOSFET to check. Now the problem here is that I've reassembled the laptop. However, I can cheat a bit here because what I know is we're going to go through these two MOSFETs, through the board, and then into another MOSFET on the other side. So if I touch one of my probes here, I know I'm getting one side of the MOSFET on the other side of the board. And then once we go through that MOSFET, we become the main power rail. So if I come over here and put my other probe on this capacitor again, we're getting the other side of that MOSFET. So let's check that. And there you go. There's our 1/2 volt diode drop through the other MOSFET. And I'll just reverse my probes and we should see over limit. So put my red probe there and check this guy. And yeah, we're over limit. Cool. If these MOSFETs had failed, as I mentioned, we would expect to see them shorted. So what we would see is a 0 volt drop through the MOSFET. And your multimeter will probably beep indicating a short circuit. And under those conditions, you would need to replace the DC in MOSFETs. However, these ones are absolutely fine, so lucky escape here. I don't have to worry about them. Okay, right. I've done a quick reassembly on that. That's most things in. I need to come back and put in the SSD and stuff like that, but this is good enough for us to turn it on and see if it works. So I'm going to carefully turn that over. There's a good chance that the battery is flat, so I don't think we're going to get anywhere here, and I'm going to have to go and find a charger, but I'll try my luck anyway. Here goes nothing. Okay, we have a power light. That's a good start. And it's going to take it a while to do anything at all because it's going to round train after having the battery disconnected. So I will talk for a short amount of time and then I'll probably just time skip to the point when it does post. The time skip is happening now. There we go. Right. CMOS is reset. Restart the computer. Sure. However, already you can see that it now turns on, which means basically we win. So I'll just let that boot up one more time. It should drop into the BIOS setup. And at this point, we can then say all is well. Long-term testing is needed, obviously. We need to leave it turned on for a bit, just make sure it doesn't conk out. Usually at this point now, I'll put the screws in the laptop, move it to another bench for servicing, where I'll do Windows update, virus checks, that kind of thing. And if it gets through all of that without conking out, I then assume that it's all working. Boot device not found. Yeah, that's because we didn't put it in. All right, you know what? That's good enough for me. Right. So that was another straightforward case of a dead capacitor. However, we've gone through that fairly exhaustively. Coming up in the future, I really want to reboot my Board Repair Basics series. And during that series, we're going to do similar kind of stuff to this, but I'm going to go into more detail about what is a capacitor? What are the capacitors doing? The capacitors that we replaced, why are they there? What do they do? Why do they fail? Those are the answers that I want to go into, as well as how these regulators actually function. So hopefully, if you enjoyed this and you want to know more, stick around for that series. It's going to be coming up next year. And hopefully we can dive into this together, because this is a very frequent fault that you'll see me doing a lot, and you'll probably see other repair channels doing a lot. So hopefully we can get a bit more into how to actually do it yourself. Thank you everyone for watching, and I'll see you all next time. Bye for now.